Now, dear student, chapter number 4, motion in plane, and today we have the topic uniform circular motion and the following subtopics which I have added here. First, we want to be discuss the basic define of the uniform circular motion. What are the basic examples of the uniform circular motion, along with the sum of the physical quantity, those having the close relation with the uniform circular motion. So first we want to discuss the angular displacement, what the actual meaning of the angular displacement we have. Second, what do you mean by the angular velocity? Now, what is the basic meaning of the time period? That mean for a particle that moving on a circular path in the two dimension. Now, frequency, what is the basic relation between the angular velocity, frequency and the time period? And what is the basic relation between the linear velocity and the angular velocity? Later on, we will discuss the statics of the uniform circular motion with the reference of the centripetal acceleration, its derivation, and along its direction. Now, in the first lecture, I am discussing the uniform circular motion. So what actually the uniform circular motion? So simply we have the basic define: a particle is moving on a circular path of a radius r and covers the equal distance in equal interval of time. That's we can say that the particle is moving with a uniform speed and covers the equal distance in equal interval of time is called the uniform circular motion. So what are the basic examples of the uniform circular motion we have? That's one of the basic exercise. So we can say that the motion of a point on the rim of a wheel rotating uniformly, that is an example of the uniform circular motion. uh, an athlete is moving on a circular path can have the uniform circular motion. That is an example. Okay, so the motion of a tip of the second hand of a clock is also a concept of the uniform circular motion. So many general examples of the uniform circular motion you have. uh, uh, you can add the uniform examples of the uniform circular motion. So one of the basic define of the uniform circular motion: if a particle moves along a circular path with a constant speed means it covers the equal distance in along a circumference in equal interval of time, then the motion is said to be UCM. That is called the uniform circular motion. So two general example which I have included here. An athlete is moving on a circular track with a uniform speed as an example of the uniform circular motion. The motion of a point on a rim of a wheel rotating uniformly. So these are the general examples we have. Now we want to discuss the basic terminology that is having the very much close concern to UCM, that is called the angular displacement. Angular displacement. So generally the symbolic notation is the delta theta. So we are just assuming that a particle is moving on a circular path. Initially it is at the point P and that moving towards the point Q. Now here we have the radius vector that is called the R. It's the center of the point circular path. Okay. So here we have the timing that is called the t1. Here we have the timing that is called the t2. So in the given interval of the time we have the basic concept that is called the delta t. In the given interval of time, that is called the t2 minus t1. It makes an angle that is called the delta theta, or simply we can say that the angle which is made by the radius vector in the given interval of time is called the angular displacement. Here we can assume the p to q is simply the arc delta s. So the angle made by the radius vector in given interval of time is called angular displacement, and delta theta is equal to arc upon radius. So we can state that delta s upon r. So this is the general formula we have. Now what are the two basic information about the angular displacement? First is unit. So it having the unit called, that is called the radian, and second one is dimension. So it is an exception quantity which having the no dimension, that is called the m0, l0 and t0. So this is the basic concept of the angular displacement we have. Now next we have the angular velocity. Dear student, in the linear motion we have discussed the several things like displacement, velocity, acceleration. So same how as the particle is moving on a circular path, so we have the analog physical quantities. Comparative to displacement we have the angular displacement, comparative to velocity we have the angular velocity, and comparative to acceleration we have the angular acceleration. So these quantity having the following relations. Now angular velocity, that is called the time rate change of the angular displacement is called angular velocity, So we are just making the concept of the average, so we are just assuming delta theta upon delta t. Okay, so somehow we are just approaching the time interval delta t tends to 0. So what can modification, what kind of the modification we can do here? Now omega will be represent as instantaneous angular velocity, and we are just assuming that limit delta t, sorry, omega is equal to, that is called the instantaneous angular velocity, limit delta t tends to 0, that is called the delta theta upon delta t, and finalize we can state that first derivative of the angular displacement. So omega is the comparative of the velocity angular displacement. So this is the general formula we have. Okay, now we are just assuming the unit. So what is the possible unit we have? That is called the radian per second. Okay, this is the unit. And what is the possible dimension we have? Dimension is m0, l0 and t minus 1. This is the possible dimension we have. Now we have the time period. So what actually the meaning of the time period? Time taken to complete one revolution during UCM, that is called the uniform circular motion, is called time period. And the symbolic notation is the t. So what is the possible unit we have? That is second. And the dimension we have m0, l0 is t1. This is the possible representation of the time period we have. Now next we have the frequency. Number of the revolution completed in 1 second is called the frequency. Okay, so we can assume the simply formula of the frequency. Frequency is equal to number of revolutions on a circular path, that is to be divided by time period. So we are just getting the formula. So possible unit we have of this physical quantity, that is called the 1 upon second, and 1 upon second generally makes the hertz. Okay, now the second is called the dimension. Dimension is called the m0, l0 and t minus 1. So this is the general representation of the frequency we have. Now relation between, it's one of the general topic we have. Relation between we have, that is called the angular velocity, that is omega, frequency nu and the time period. Okay, so we are just assuming the case that the particle is moving on a circular path. Okay, so it makes an angle in a one revolution. So it makes an angle that mean this is the call of the delta theta, and this one is the that delta s. This is the p, this is q, this is the center o. So we are just assuming the relation, that is angular velocity, that is called the delta theta upon delta t. Here we are just assuming the standard the notations, that in a one revolution the total angle which is made by the particle, that is called the 2 pi, and the time taken to complete the one revolution, that is 2 pi, that is capital T. So omega can be stated as 2 pi into 1 upon t, and 1 upon t can be converted into frequency. So omega is equal to 2 pi nu is the, that means one of the basic relation we have. Now we have the next, that is called the relation between linear velocity and angular velocity. Linear velocity and angular velocity. So what actually meaning we have? So we will discuss the formula. Now we are just saying that delta theta is equal to delta s upon r. Okay. Now this is the equation number 1 we have. Dividing equation number 1 by delta t on both sides. So what we are getting, delta theta upon delta t is equal to 1 upon r delta s upon delta t we have. So this is the one of the general representation. Now we are just approaching the limit on the both side. This is the equation number 2. Limit delta t tends to 0, that is called the delta theta upon delta t, that is 1 upon r. Limit delta t tends to 0, that is called the delta s upon delta t. So this is the part of the derivative we have. So we can substitute the whole term by the simply meaning that dy by dt of theta, that is called the 1 upon r is equal to dy by dt of the s we have. Okay, now we can state about the dy by dt of theta as the omega, and 1 upon r, and displacement upon time can be simply the velocity. Okay, so we are just making the cross multiply, so we are just getting the relation, that is v is equal to omega r. Okay, this is the one of the desired relation we have. This is called the linear velocity. Linear velocity. This is called the angular velocity. This is called the radius circular path. Okay, now whenever we are just we are just getting the proper knowledge of the vector notation, so cross product can be represented by, that mean v is equal to omega r. So later on we will discuss the vector product. So on that time we will discuss that how can we discuss this one relation. Now one of the another analog term we have, that is called the angular acceleration. In the linear motion we are just simply studying for a linear motion, that is called the acceleration, and on the circular path we are just discussing the angular acceleration. So time rate change of angular velocity is called angular acceleration. Angular acceleration. Okay, so somehow we are just making the, that mean concept, average angular acceleration, that is called the delta omega upon, that is called the delta t. Okay, this one is already the simple nomination we have. Now instantaneous, as the time interval approaches to 0, so what will happen, the angular acceleration, the average angular acceleration will be termed treated as a instantaneous angular acceleration. Okay, so alpha can be stated as limit of delta t tends to 0, delta omega upon delta t, and that is called the dy by dt of omega. So somehow we are just getting the symmetry of these kind of the formulas, those we have discussed in the linear motion. So this is the one of the basic relation we have. Now somehow is anyone is asking that what is the unit and the dimension. So on behalf of the unit we have radian per second square, radian per second square, and the concept of the dimension we have m0, l0 and t minus 2. It's a basic concept of the dimension we have. Now relation between the linear velocity and the angular velocity we have. So somehow we can discuss the uh, relation between a is the acceleration and alpha is the angular acceleration we have. Now relation between v and omega. So already we have discussed v is equal to omega r. This is the one of the relation we have. This is the equation number 1, and now we are just dividing the equation by the derivative, that means dy by dt on the both side. And here I am also representing the r is equal to dy by dt of the concern of omega. Okay, so here we have the special meaning, that is called the acceleration. Thus the r and dy by dt of omega is called the alpha. Okay, so this is the basic relation we have. A is equal to r alpha, or a is equal to alpha r. Somehow we are just representing in the vector notation, vector product. So we are just representing a is equal to alpha vector cross r vector. So these are the example of the vector product we have. Okay, so we have discussed the few quantities, those having the close concern with the uniform circular motion. First we have discussed the angular displacement, second is the angular velocity, third is the angular acceleration along with the time period and the frequency. So how can we utilize this one information in the uniform circular motion? As we have to be discussed, we have to be discuss the formula of the centripetal acceleration and the uniformly accelerated motion.